Hey, what's up? It is April 18th, 2021. April's winding down, and the Sugar from fairies are asleep right now, but they'll be out later. Um, so, with that being said, let's pay tribute to them by walking through their forest and trying to prune a tree. Or at least let's figure out if we can learn something about their trees. Okay, so this is problem 333, largest BST subtree. It is a pretty well-liked problem, 10 to 1 like to dislike ratio, and it is somewhat of a classical computer science problem. So what I'm going to do today is I'm going to go through the most intuitive solution. I'm not going to really optimize too much because I want to just break out the basics on how to do it. I want to give you some info and show you, the logical steps, and then we can figure out how to optimize at another point in time. So with that being said, let's start. Okay, so given the root of a binary tree, find the largest subtree, which is also a binary search tree, where the largest mean subtree has the largest number of nodes. So this is actually a combination of two problems, okay? The simpler problem is just find whether a tree is a binary search tree or not, which is a classical problem in computer science. So subtree must include all of its descendants. So what's the difference between this problem and can you find whether the tree is a binary subtree? Well, some subtrees of your initial tree may be a binary subtree, right? So your initial tree in this case is a tree of size 6, but only the 158 or 518, however you want to phrase it, is a binary subtree. And so if you can imagine a much larger tree with several more nodes, then the potential for many of those subtrees to be binary subtrees are there, though you want to find binary search trees, not binary subtrees, but you want to find which is the largest of all the binary search subtrees. So you can have a tree that looks like, be a good drawing. Whatever. Just figure these are roots. It's not a good drawing here, but good enough. I think you can kind of get my tree art here, my tree ASCII art. Here, let's drawing these all with parentheses. Just pretend each of these parentheses is a node. Okay. And, again, you can have many search trees here, and maybe this right here, this is a search tree, this from here to here, and maybe this is a search tree. 1, 2, 3, 1, 2, 3, 4, 5. So this subtree, if this is a binary search tree, is larger than this of 5 nodes, is larger than this subtree here of 3 nodes, which is a binary search tree as well. Okay, so again, you could have another binary search tree 1, 2, 3, but these two not being a binary search tree, just given the numbers. And remember the property of the binary search tree. All the nodes have to have the left child always less than the right child for every descendant as well, and the right child always greater than the root for every descendant as well. Okay, so not just enough to have the immediate parent and the children be adhering to the binary search property, you need every descendant. And that's why this larger tree here is not a binary search tree, because all of its descendants don't adhere to the binary search property. Why is that? Because take a look here. 10, 15, 7 is not, this 7 violates the binary search property. If this was 20, then this entire tree, 10, 1, 5, 8, 10, 15, 20, would be a binary search tree, and it would be the largest, in fact, larger than this sub-search tree, which is 1, 5, 8. So that would be a search tree of size 6. So Let's figure out how to do this. So, firstly, I want to search my space of trees. So that's where I'm going to go. So I'm looking for a max value here. Okay, that's why I'm putting this in max here. And as I search, I want to pass this max through because I'm going to want to find out what the max is recursively somewhere, and somewhere nested within the largest tree it could be. So firstly, let's write out my actual DFS function, right? So this is the top level search. This is the actual searching my entire tree space, and I'll explain the idea here, but there is a little bit of this is a search within a search, okay? So if root equals null, and return. Now, what I want to do is DFS before I'm going to do a pre-order traversal. Root.left max and root.right max. Okay, so now what goes into the meat of this function? That is the million-dollar question, right? Because that here is where I want to determine if my tree is a binary search tree or not. Okay, so remember, in order to determine whether a tree is a binary search tree, and remember, a subtree of a non-binary search tree can be a binary search tree. So that's why we're going to have to do a recursion within a recursion. So firstly, what I'm going to do, size equals, okay, I'm defining a 0 size node. So I'm taking advantage of a lot of functions here, or a lot of arrays that I can pass through. You might be wondering, if you're not familiar, as to why I'm defining this boolean and this int size, and this boolean is BST as an array rather than just a value, because it's the way that Java works. I want to pass these by value, by reference, so I can have the entire search process, regardless of what recursion frame I'm in, aware of the recursion, the state of the stack. Okay, recursion stack. And this is a common trick, and this is a pretty powerful trick actually, right? Because if this was a boolean, right, and this was just a primitive value, then every recursion would not maintain the state. That would be passed by value, by the mechanics of Java, and when you pass something by value, you're not changing the original object. So isBST would always be starting, even though isBST may be true somewhere in the array, somewhere in my search stack, I would never know what the global isBST, because isBST would be a copy that I passed through, rather than a reference to the original global variable. So you can think of this as like a locally global variable. That's just for those who haven't seen this before. So now I have a function here. I'm keeping, I also have this previous value here. I'll explain that in a second. But I have this, so, and in fact I could probably optimize this. I don't think I need, I'll try this in a second. So, I'm now doing a search for this particular tree, whether it's a binary search tree. Now, this is why this is a recursion and a recursion, because this isBST is another function that I have embedded within another search, which I have embedded within my standard DFS. Okay, trust me on this. If this is a little confusing, hopefully it'll make sense in a bit. isBST, okay, max equals math dot max 0, size 0. Okay, now I'm determining whether what my max BST is up to this point. Okay, now let's write the isBST function. Okay, now that I have the actual skeleton, I can write my second recursive function in here. And just think why I would need a second recursion here. I invite you to think about how BSTs and sub BSTs work. Okay, because you know, you'll see that I will need to do this because, again, I'm always going to have to doubly recurse through the search tree. So you can think of this already as being an n-squared algorithm, right? Because essentially, this is kind of the way, if you're familiar with recursion, this is kind of the way, or iteration, this is kind of the way you do like nested loops and iteration, recursion within a recursion in many cases. So now I have my is BST, my recursive end condition, right? My base case. Now I need to keep track of the size of the BST as I iterate through, because I want to know how big it is up to date, up to this point. Okay? So I have my size variable, and if I have, now this is, you'll understand this in a minute, but how do you find whether something is a BST or not? Okay? This is what's called an in-order traversal. All right, this is back to basic CS. I'm going to so whether something is a BST or not depends on, for example, when you turn that BST into an array, 3, 4, 5, 3. Let's see, what's a 9, 5. So up to this point, this is a BST, okay, because this tree is ordered, okay? Like, so the thing is, you have to understand what is a sub BST, or what a BST is. Like, if I perform my in-order traversal and I get something like this, right, as the output of my in-order traversal, then this is not a BST, because a BST will always, the reason why it's efficient is because it lets you search everything in order, okay, from left to right. You can construct a sorted array out of a binary search tree, okay, by simply recursing through it. That's the nice property. And again, I would invite you to look at in-order traversals to understand why that works. But basically, as I iterate through the tree from left to right, because I'm doing a pre-order traversal here, 1, 5, 8, 10, 15, 7. These numbers, 1, 2, 3, 4, 5, will be in order, right? That's just the way because that's just the way the BST is set up to this point for sure. And it would have been a full BST if I was able to go down here and call this this tree, this 7 something like 20 or something. Then all of these would be in order: 1, 5, 8, 10, 15, 20 in order of traversal. Okay, that's important to let it sink in. So how do we make sure that's the case? So what do I have to do in my in order step to make sure that this is the case? So you might have noticed this previous node here. Okay. So basically, how do I check if my in order traversal is going to be in order, so to speak, right? In sorted order. Is it going to? I could do something like make an array, right? Where everything, and then check the array, but that's slow. Why would I need to save everything to an array? So that's what this previous value here is, okay? Because I can always, and that's why I made this previous value something I pass by reference, because I can always understand the state of, the absolute state of this tree, or this traversal, whether so far the elements I have is in order, if I just look at the previous element, right? Because the previous element will have to be less than or equal to the current element. Okay, so if the previous element is null, that means we haven't traversed anything yet, right? And that's why over here I start the previous element in null. Okay, it's a null tree node. Then the next element will be root.val. I'm always at root.val, and I need to check the previous element. So that's why after the recursion is done, I save the root, or after the in-order work is done, I save the root to previous, so that the next recursive call wherever it is in the recursion stack was aware of the previous node that I had visited. Okay, let this sink in a little because this is a very useful way of searching for a binary search tree, or just without searching whether a tree is a binary search tree without having to write out the entire array or do anything more fancy. So let's run this. Let's see where I'm at so far. Okay. Okay, so that looks like it worked. Okay. And I'm going to run this on this test code. That looked like it worked. So let's see. Let's run it overall. Okay, pretty slow, right? Because look, I'm doing a recursion within a recursion, so I'm doing n squared work. You know, because every tree that I recurse, subtree is another uh, another loop. Because if I only did the one DFS, the work would be O of n, right? O of n. But each of this BST here is also O of n. So, and even though it's decreasing, because in every turn it's O of n minus 1, O of n minus 2, etc. According to Gauss's first theorem, and we're not going to go into the details, but basically this is O of n squared algorithm, okay? So, now how are we going to make this a little faster, okay? Well, firstly, I can note that since we're doing repetitive recursions and we want to make sure that we're essentially looking at smaller trees on each recursion, right? I can maybe already see that if I've already gotten a tree greater than the size of a tree that I search later on, then there's no point to continue at all. So putting this here, if max 0 is greater than size 0, at this point I found my largest tree here. There's no reason to continue because I'm always going to get smaller and smaller trees as I go down there's no way that when I go down the levels of the tree that I'm going to find a larger tree than a higher level, right? So if I've already found my max and it's greater than the size of the next tree that I search, then there's no reason to go smaller and smaller because there's no possible way I can get a larger tree. So let's try this optimization and see what it looks like. There you go. Much faster. Okay, 0 milliseconds. But problem was the space isn't that great. That's probably because I'm doing a lot of extra recursive calls. Now I could probably turn this into that's a better n squared operation. It's still on the order of n squared, really. Probably maybe there is a order optimization there, but either way, there's probably a faster way of doing this.